Professor Christine Charles is head of the Space Plasma, Power and Propulsion Laboratory at the Australian National University. She is the inventor of the Helicon Double-Layer Thruster, a new type of space engine with applications to satellite station maneuvering and interplanetary space travel. She generously agreed to be interviewed about how physicists view and work with unknowns. Christine, thanks for agreeing to be interviewed. There are two sort of stereotypical views about physics, I think, with the lay public. On the one hand, it seems like the most certain of sciences, and so a lot of people tend to think of physics as having uncertainties that are only perhaps in very tiny imprecisions in measurement, on the one hand. On the other hand, physics seems to contain some of the biggest mysteries of the sciences, such as what is dark matter or what state the universe is headed towards. Can you say a few things about the sorts of unknowns that physicists would typically deal with?
Perhaps it would be good to start with a bit of a background on the scientific method. So I would say that in the 10th century, an Arab called Al-Hazan developed the first major work on optics. So he can be thought of as the first to explain refraction, light refraction, and to develop the precursor of Snell's law. But most importantly, he argued the importance of forming questions and testing them. In the 15th century, Francis Bacon proposed the inductive version of the scientific method. So this means that you observe nature, you try and develop models to describe generalized patterns or observations, and then you confirm by more observations. So perhaps the simplest example of a scientific experiment would be that, for example, you would just drop a ball from different height and you would measure the time it takes to reach ground. And you would repeat this the next day, and you would repeat this in another country, and you would try and have different people repeat this. So it is important to say that theories cannot be proven. They can only be falsified. This is why they really need to be scrutinized by experiments.
So tell us a bit more about doing experiments and why you do experiments.
This is a very important question, because a lot of people think these days you don't really need to do experiments anymore. You can just program things on a computer and things will happen. But for me and for most physicists, we are very curious. We want to find out how it works, why it works or why it doesn't work, and experiments is there to tell us the truth.
And are you looking for things that you already know, or are you looking for things that are unsurprising and new?
So usually you have to prepare, so you kind of want to know what is going to happen. You expect some things. But the best is really when you get surprised by the experiment. And then, number one, you have to try and repeat the experiment. It's even better if other people can repeat the experiment. And you have to try and falsify it or disprove it and continue along this process.
Now, your area of specialization is plasma physics, isn't it? So can you tell us something about, first of all, what a plasma is, maybe give some examples, and what sorts of unknowns you encounter when working with them?
So plasma is usually referred to as the fourth state of matter. The easiest way to explain it is to use the example of water. So if it's very cold, below 0 degree, you have water in the form of ice. So this is solid, the first state of matter. Just imagine you grab 2 ice cubes, and this is number 1 state. You want to put energy into this system. So you're going to rub these or put them in your warm palms. So it's going to start melting. You will reach the liquid phase, which is the second state of matter. Now this water, you can put it on a stove and boil it by putting energy into it, and you get water vapor or gas. This is the third state of matter. And you can keep putting energy into this system, and eventually you're going to start dissociating and ionizing your water molecules. So when you ionize, electrons are stripped off your molecules and you end up with a positively charged species, which is called the positive ions. And you get a water plasma. So this is the fourth state of matter. You ionize your gas. So your gas is becoming ionized and is being heated. And you can actually keep going. You can take all the electrons off, and eventually you will have fusion between the nuclei. So these would be the hottest plasmas that you can get. For example, fusion of hydrogen in the core of the sun. So plasma is the fourth state of matter, a hot ionized gas.
And so what are the unknowns that drive the work that you do?
So you have a lot of particles and they have different temperatures. So a lot of it is due to statistical distributions in energy and in temperature. It's a little bit like having an immense crowd of lots of different people from different cultures, and they will all react differently depending on, you know, how they feel. So it's just a big soup of really active species with lots of different temperatures and movements. So the uncertainty is about finding out how to represent the different species, and usually we use temperatures or velocity or parameters such as those.
So one of the things we're interested in is the relationship between ignorance or unknowns and creativity. Now you've developed plasma propulsion. Can you tell us what that is and how it works and how the creative process worked?
Yes, so I have developed what is called the Helicon double-layer thruster. So it's a new form of plasma engine for space travel to be used on satellites or future spacecraft for interplanetary exploration. It is based on a basic research experiment. So it was the second step was the development of the thruster, but at the heart of it was to try and explain the physics of expanding plasmas. So we have explained that plasma is the fourth state of matter. So you create a plasma in a bottle and you let this plasma expand in the universe or in a bigger bottle or in space, and I was trying to understand the physics of this. And I was interested in adding a diverging magnetic field similarly to what happens at the surface of the sun. At the surface of the sun, you have the solar corona, which is this halo that we see when there is a full solar eclipse. And these funnels are at the origin of the solar wind. That's where the solar wind originates from. And this solar wind is accelerated before it expands into the universe. So I was looking at this acceleration process. And this is how I found that there is a form of shock that can spontaneously be created within the plasma. So that means that all your charged particles or charged ions in your plasma will see this shock and they will get a kick and they will be accelerated. And what will leave this funnel is a collimated supersonic ion beam. So this was the actual physics. Once it was shown that there is an ion beam, then it was kind of immediate to think, okay, I can use this as a source of propulsion for this new concept in plasma propulsion.
So can you just say a little bit more about the creative process itself? I mean, it sounds like you used a bit of analogy about what's happening in the sun anyway, but what was it, where did the idea come from? What led you to develop it?
At the time, I was actually doing a music degree. So I had less and less time for physics, and that was concerning me a little bit. I'm thinking, oh, I must not lose grasp with physics. I need to just... And I was always interested in expanding plasmas. You have this ball of light and charged particles. If you just let it go, what will happen? So I wanted to study the different modes of expanding plasmas. So I set up an experiment and just was changing the knobs, just wanted to find out and just be connected with physics, just the love of physics. And that's when I found it. I found this non-linear process, curious process, which I was not expecting. However, when it happened, I knew that, I had read enough that I knew that it was possible for this to happen. So I immediately was able to use it and manipulate it. So that was the process. I had an idea of the experiment, it was driving me, and I was surprised by the experiment. So I went back the next day to try it again, and yes, I saw it again the next day, and now a lot of laboratories have validated this concept, so we hope that we have followed the right procedure.
So in this case, you were surprised, but you also had the background knowledge and preparation to know what it was you were looking at.
Yes, because many years earlier I had seen what I thought was a signature of the effect, but it was just tiny. Perhaps, I was worried by the error bar. This is just maybe error, uncertainty, and I couldn't prove it then. So I always had it in the back of my mind. So when it happened, it was amplified by one order of magnitude at least, and I thought, okay, it really probably was there back then, and now I have made it much stronger. The experiment has had the right conditions to do it, and it's a spontaneous phenomenon. It's really neat. It's like if you give it the right ingredients, it will do it, a bit like cooking. If you don't give it the right ingredient, it's just not going to work.
So the final frontier is not space, it's plasma.
Or both, or maybe there are lots of different frontiers. Something very interesting we did with plasma is that you can grow different materials. So we actually used plasmas to deposit nano clusters of catalyst on top of plasma grown carbon nanofibers, and we managed to make small hydrogen fuel cells using this. And hydrogen fuel cells can be used in transportation. You have fuel cell cars. So we are looking at ways of trying to help with the energy crisis, because we will have an energy crisis. So there's a lot of material science that can be done with plasmas.
So plasma physics meets nanotechnology.
Oh, definitely, definitely. Because you can use the ions and electric species react to electric fields and magnetic fields. So you can use the ions to help with the surface process that you are working on.
So that sounds as if it really actually is going to revolutionize material science.
I would say it already has revolutionized material science. In the microelectronics industry, the revolution occurred in the 1970s. A computer used to be the size of this room. Now a computer as powerful as this is what I have in my phone, and this is only thanks to plasma technology. Because with plasma technology you can etch, you can sputter, you can deposit materials at a nanoscale or nearly nanoscale, and so you can reduce the size of the transistor. So instead the first transistor was quite big, but now you have millions of transistors on a really small surface, and they are very, very performing transistors. And this is only thanks to plasma technology, because before plasma technology, people were using liquid, the second state of matter, to dig holes and make wires for conducting the information and all of this.
That's fantastic. Thank you very much.
Oh, thank you.